Hello! Our third and last video about sequences will explain geometric progressions. Again, we will start by defining what's a geometric progression. Again, it's a type of sequence. But now, the difference with arithmetic progression is that each term is obtained by multiplying the previous one by a certain quantity. So each term equals the previous one multiplied by this fixed quantity. This fixed quantity is called ratio. And again, I have here the recurring law. So to recognize a geometric progression or geometric sequence, for example, if I have 3, 6, 12, 24, 48, to be a geometric progression, when I go from the first to the second one, I can check I multiply by 2. And again, when I go from the second to the third term, from the third to the fourth term, I'm always multiplying by the same quantity. So this is a geometric progression with ratio equal to 2. But don't let you mistake, because, for example, here I could say, when I go from the first to the second, I'm dividing. No. In geometric sequences, I always have to multiply. It's the same that when the difference is negative in arithmetic progressions. When I go from the first to the second one, yes, I'm divided by 2, but it's the same that saying I'm multiplying by 1/2. If I write here divide, it's not a geometric progression. I have always to say I'm multiplying by the same quantity. In this case, is 1/2. Okay? So, as I did with arithmetic progressions, first of all, I have the recurring law as an equals to na minus 1 multiplied by r. For example, if I have the sequence I wrote before, I'm always multiplying by the same quantity. So, if I want to write the general term, each term can obtain from the first one by multiplying by r how many times. To obtain the second term, I have to multiply once. To obtain the third term, I have to multiply by r twice. When I have the fourth term, I have to multiply 3 times. I always have to multiply by r n minus 1 times. So now n minus 1 appears as exponent. In this case, the general term can be calculated by multiplying 3 by 2 multiply n minus 1 times. This way, for example, I can calculate a 11 as 3 multiplied by 2 to the 10th. Okay? When I have very big numbers, I can just write 3 multiplied by 2 to the 10th. you don't have to calculate 2 multiplied by 2 multiplied by 2 multiplied by 2 10 times, because it's something completely absurd. Okay? And to end with geometric progressions, I'm going to add again the n first terms of a geometric progression. I'm going to add all of them, and the formula is Sn equals the last one multiplied by r minus a1 and all divided by r minus 1. So, for example, with the sequence I have been studying, I want to add again the first 20 terms. I know the ratio equals to 2. The first term equals to 3. And I also need the 20th term, which can be calculated as 3 multiplied by 2 to the 19th. So the addition of the first 20 terms will be 3 to the 19th multiplied by 2, which is the ratio, minus 3, and all divided by the ratio 3 minus 1. In the numerator, I can extract 3 as common factor, to the 10 minus 1 halves, and I don't need to calculate. Here I have a special situation. What happens if r is lower than 1? If r is lower than 1, remember the general term is the first term multiplied by r to the n minus 1. When I multiply a number lower than 1 but positive as many times as I want, this number is as small as I want. So in the limit, this term tends to 0. So a to the infinity, to write in some way, would be 0. In this situation, I can add all the terms of this geometric sequence, this is written this way, as the first one divided by 1 minus r. And it's only possible if r is a number placed between 0 and 1. And that's all I have to know about geometric progressions. Tomorrow at class we will do exercises about all these contents. But that's all you have to know before the exam.